In this presentation, we will explore the nature of multiphase and high-frequency electricity and its effect on X-ray generation. Additionally, we will outline how the higher quality radiation it produces will affect the final image and patient dose. If you aren't familiar with how Bremsstrahlung breaking radiation is produced or the basics of AC power, you might want to review these lessons before viewing this one. Let's take a few minutes reviewing some of the important facts regarding X-ray production. X-ray production is caused when high-energy electrons interact with the target material's nucleuses. In diagnostic radiology, the bulk of X-rays are produced by Bremsstrahlung interactions. It is important to know that the maximum energy that is imparted to an X-ray cannot exceed the energy of the particular electron which creates it. A 30 kV electron can only produce a 30 kV X-ray at most. And it is very likely that the 30 kV electron will produce an X-ray with less than 30 kilovolts of energy. In the X-ray circuit, the AC waveform is maintained to accommodate the operation of the high-voltage transformer. Just before current is sent to the tube, the AC is converted to pulsating DC by the rectifier bridge. Below is a schematic representation of the rectifier bridge. The waveform below illustrates the voltage applied to the X-ray tube by a full-wave single-phase DC generator. This line denotes the kilovoltage peak that is selected by the radiographer. Note that this line indicates the maximum energy any X-ray produced by the generator can have for this particular exposure. Additionally, note that the minimum energy this generator will produce is 0 kilovolts. And if you look along the waveform, all the kilovoltages below the maximum will also be produced. This means that the voltage applied to the tube will vary by 100%. And there are times that the generator produces no X-ray at all during the exposure. Let's draw a line at 20 kV and shade the area in. X-rays produced at this voltage or lower have little chance of penetrating the patient's tissues and contributing to image formation. They mostly contribute to patient radiation dose. There is a partial solution to this problem, and that is to use three-phase electricity to power the generator. Three-phase power consists of 3 waves of power sent to the generator 120 degrees out of phase with each other. This wave represents a cycle and a half of power. At 120 degrees after the first wave begins, a second wave is sent to the generator, renewing the voltage push of the electrons through the tube. At 240 degrees, a third wave of electricity is sent to the generator, giving another push to the electrons sent to the tube. We now have 3 overlapping waves of AC power sent to our generator. All that needs to be done now is to flip the reverse waves using a rectifier bridge to convert them to the DC waveform. The X-ray tube needs to function properly. Note that as each wave is reversed or flipped, the peak of the wave falls halfway between the peaks of the other 2 waves. What we end up with is a confusing jumble of overlapping waves. I'll mask out all of the superfluous portion of the waves and illustrate the important portions that actually do the work of producing X-rays. Note the kilovoltage no longer is allowed to drop to 0. Rather, the kV rises to the selected voltage value and only drops to 15% of the maximum, greatly improving the average energy of the radiation produced, but also getting rid of times when the X-ray tube is not producing any radiation at all. Now we are producing 3-phase, 6 pulses of radiation per phase. The benefits and costs of 3-phase generators are: it yields a higher quality radiation with more image-producing radiation. Since the kilovoltage across the tube never drops to 0, more radiation exits the tube at the given MAS level, so the MA can be reduced by 30% or shorter exposure times can be used. One drawback of 3-phase power is it's more expensive to purchase than single-phase, and the generators are more expensive to build. Beginning in the early 1970s, there was a need for X-ray generators that could provide rapid sequence filming, and 3-phase 6-pulse generators were not up to the task. So 3-phase 12-pulse generators were developed. This generator takes each phase, divides it in half, and offsets the phases by 60 degrees. Below is a 3-phase 6-pulse waveform. Add a 4th wave, a 5th wave, and a 6th wave, and you get something that looks like this. If we again hide the extraneous portion of the waves, the input voltage of the tube looks like this. As one might expect, the voltage drop varies by about 7%, or 1/2 the amount of variation of a 3-phase 6-pulse generator. This is an example of a 3-phase 12-pulse rectified waveform. Pros and cons of this system are: 12-pulse power produces a higher quality beam than a 3-phase 6-pulse, but not a big difference. 40% more radiation output than single-phase unit, which is 10% more than a 6-pulse generator. The generator is more complex and expensive to build than a 6-pulse unit, but uses 3-phase electricity, so day-to-day operation costs are not much more. Modern X-ray machines use high-frequency generators that produce a waveform that varies from 1 to 400 kHz. This is made possible by the development of components that can handle high-voltage currents typical in an X-ray tube. In these generators, the variation from the selected kV is little indeed. About 1% variation is typical. Pros and cons are: the difference between 1% and 7% variation in voltage is small, so the beam will be a better quality compared to 3-phase 12-pulse, but the difference is almost negligible. The radiation output of these generators is about the same as 3-phase 12-pulse generators. The initial cost of the high-frequency generator is higher than single-phase or multi-phase generators. These generators can run off single-phase power, making their day-to-day operating expenses much less. To summarize, the advantages of multi-phase or high-frequency systems are: at any given MA station, you can expect to receive 30 to 40% increase in the radiation production compared to a single-phase unit. One way this is helpful is that it can reduce exposure times and reduce the chance of motion artifact, or enable high-speed filming. More MA output translates to brighter fluoroscopic images. While multi-phase high-frequency doesn't eliminate low kV X-ray production, it does reduce the likelihood of low kV X-rays being produced, increasing the quality of the beam. Higher quality radiation, which means less patient dose and higher contrast resolution for every exposure. This will end my presentation. Thank you for your attention.